Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline, you'll need somewhere to deploy it, so check out Linode. With private networking, shared block storage, node balancers, and a 40 gigabit network, all controlled by a brand new API, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today to get a $20 credit and launch a new server in under a minute. And you work hard to make sure that your data is reliable and accurate, but can you say the same about the deployment of your machine learning models? The Scafos platform from Metis Machine was built to give your data scientists the end-to-end support that they need throughout the machine learning lifecycle. Scafos maximizes interoperability with your existing tools and platforms and offers real-time insights and the ability to be up and running with cloud-based production-scale infrastructure instantaneously. Request a demo today at dataengineeringpodcast.com/metis-machine to learn more about how Metis Machine is operationalizing data science. And the team at Metis Machine has shipped a proof of concept integration between the Scafos machine learning platform and the Tableau business intelligence tool, meaning that your BI team can now run the machine learning models custom built by your data science team. If you think that sounds awesome, and it is, then join the free webinar with Metis Machine on October 11th at 2 p.m. Eastern Time, 11 a.m. Pacific. Metis Machine will walk through the architecture of the extension, demonstrate its capabilities in real time, and illustrate the use case for empowering your BI team to modify and run machine learning models directly from Tableau. Go to metismachine.com/webinars now to register. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And join the discussion at dataengineeringpodcast.com/chat. Your host is Tobias Macy, and today I'm interviewing Nikita Shamgunov about MemSQL, a new SQL database built for simultaneous transactional and analytical workloads. So Nikita, could you start by introducing yourself?
Yeah, so my name is Nikita Shamgunov. My role here is the CEO. And I have a long history here at MemSQL. And prior to that, I was at Facebook. And before that, I was a SQL Server working on the kernel. I think it makes sense to share my academic history. So I actually grew up and got educated in Russia. And my passion then was doing programming competitions. So that carried me through my high school years, then college years. And then I went into the academic track, where I went to St. Petersburg University of Fine Mechanics and Optics and did my PhD in computer science. And right after the graduation, in fact, I got an offer a few months before the graduation. I got on the plane and joined Microsoft to start working on SQL Server.
And so it sounds like that was your initial on-ramp to getting involved in the area of data management.
Yeah, absolutely. So I worked on some of the aspects of that during my PhD program. But really, the trial by fire was certainly at SQL Server, where not only I was exposed to the area of data management, but in a broader way, started working on systems. And I think there is a very specific set of skills that goes into engineering hardcore, complex systems written in C and C++ and built for performance and reliability. So certainly SQL Server was a very, very good training ground for me.
Yeah, getting thrown in at the deep end is usually one of the most effective ways to learn something very thoroughly, because it's either sink or swim, and that is a great inspiration for taking the time to fully internalize what's happening under the covers.
Yeah, absolutely. And the experience, like you said, was really going into the deep end. A few weeks into the job, when I just arrived from Russia into the United States, I was spending most of my time in the debugger, basically understanding that SQL Server kernel, fixing bugs. And at the time, we were working on stabilizing one of the most ambitious releases of SQL Server, which is SQL Server 2005, 5 years in the making, which is really unheard of in modern days. Like, nobody takes 5 years to ship a piece of software. But, again, at the time, we were on this death march of driving the quality of the product up after building a lot of features that went into that product. So that was a lot of fun, actually.
And so that was what set you on the road to ultimately working on MemSQL. So I'm wondering if you can describe a bit about what MemSQL is and the motivation for starting the project and building a business around it.
Absolutely. So MemSQL started with a few insights. And the insight number one is a several attempts of building a scalable transactional system inside Microsoft. I was not part of that effort, but my co-founder and chief architect, Adam, was. And while we were there working on the project called MatrixDB, it was an incredibly frustrating experience that we actually could not ship that thing. And then when I joined Facebook, it became very apparent to me what the power and the value of such system is. And we went on a journey to build a new database. We were very passionate about building databases and building systems. And I remember having a conversation back then. And the conversation literally was the following. Well, it's actually a lot easier to build an analytical system. But we thought that at the time, the game was over. History proved us wrong, right? Since there's a lot of cloud data warehouses came into existence. But we were looking at the market and seeing a lot of companies like Data Allegro, Vertica, Netezza, Aster Data being acquired. And so we're like, okay, well, it's much harder to build a transactional distributed system. So let's just do that. And then we went on that journey having just a few insights. A, we believed that there was more of an opening to build a scalable transactional system. Two, we saw the value of such system by looking at some of the workloads inside Facebook. Most of such workloads that we were exposed to were around real-time analytics. Basically, you need a transactional operational system to withstand high volume of inserts, updates, deletes that hitting the system. But at the same time, the value is to actually drive insights, drive analytics. And then the last insight was the unsuccessful attempt of Microsoft of building a distributed system with a starting point SQL Server. And the competition for Microsoft at the time was Oracle RAC and Oracle Exadata. And we kind of believed that there is value in building such a system. And we thought if we build it, then there will be a market for this system, because obviously Microsoft is trying very, very hard to build one. So that's how we started. And then the amount of technology that goes into a product like this is absolutely enormous. So you need to pave a path. And we made a bunch of assumptions to get to basically version 1.0 to not only build such a complex product, but being able to drive revenue on the way to the ultimate vision of being fully scalable, elastic, transactional system that can support transactions and analytics in one product. So that assumption, the first one was, let's build an in-memory system. There was a lot of research at the time about building in-memory systems. And also there's another assumption that you can make, that the cost of RAM is going to go down so dramatically that everybody will be running transactional systems in memory. That assumptions turned out to not be true. And if you compare the cost of RAM versus the cost of flash, for example, the cost of flash, dropped all the way down to the ground versus the cost of RAM. RAM got cheaper, but not orders and orders of magnitude cheaper compared to flash. But yet, in memory was actually a very good starting point for us, because it allowed us to onboard various high value workloads. So you can drive revenue with relatively small number of customers, solving exotic problems that those institutions have, and they're willing to put money and faith into a new startup to solve those problems.
And how much of your product roadmap ended up getting driven by those early customers with the exotic problems, and how much of it was a matter of going and doing customer research with people who had more standard workloads to try and figure out what was the best direction for driving the company?
This is a very good question. So the beauty of the situation where we ended up early on is the exotic angle of those problems were only around performance, but not around the surface area. So the roadmap very nicely aligned with expanding the surface area. And the surface area of a transactional SQL systems is massive. Not only you need to build your storage features and clustering features, but you also need to provide very, very good SQL support, which is a combination of just a very broad language, SQL, but also investments into query optimization and query execution, and really understanding the universe of all possible workloads and doing a very good job workload by workload and shipping new releases of MemSQL. So to answer your question, the exotic part is just performance and scalability. And then the general purpose part of having a very good support of SQL, having an extremely reliable product, and I can talk for a long time about quality of databases and systems in general. So we found ourselves actually in a decent spot where we're not torn, expanding the exotic nature of the workloads versus building general purpose features. Those kind of align very nicely for us.
And now that you have iterated and put out a number of additional releases from that 1.0 milestone, what are some of the typical use cases that you see for customers who are currently running MemSQL and people who are in conversations with you to add it into their infrastructure?
So you can parse this question and answer it in terms of tiers. So at the very, very high level, we support general purpose database workloads that require scale. We give you unlimited storage and unlimited compute. And in one product, in an elegant way, we can scale your applications, which is a very stark contrast to your existing single node systems or legacy systems, the Oracles, the SQL servers, the Postgres of the world, where the amount of storage and compute is limited. Now, this is too general. So what is the next iteration of answering that question? Well, the second one is let's look at the very specific workloads, but still wear a technology hat. The first one is real-time analytics. You have a data coming at you either through an application or through a message bus such as Kafka or in the cloud Kinesis, and you need to provide insights into that data in real time. It's supremely important to know what's happening with that data within maybe milliseconds or seconds or minutes, but in a short period of time. So, and we call this workload real-time dashboards. And real-time dashboards are important in financial markets, they're important in healthcare, they're important in packaged goods, and in Web 2.0. So real-time dashboards is something that MemSQL does incredibly well. So this is one workload. The second workload is there's a Web 2.0 workload that requires scale because of concurrency. And that's where giving infinite compute allows you to build your system with much fewer moving pieces. You don't need a cache. You don't need to shard your database. You can just deploy MemSQL and it will drive arbitrary level of concurrency for your Web 2.0 or mobile application. So we have a number of workloads like this as well. And specifically, the moment you add reporting into an application like this, you just have a much easier way of burning compute. So for example, in the financial markets, there's a number of use cases such as portfolio analysis, or wealth management, where you log in and you see your assets and reports. And generating reports burns a non-trivial amount of compute. So if you want to deliver great user experience and lower latencies, you actually need a scalable system. So that's another kind of class of applications where there's a lot of concurrency on the other end. And then finally, there's a set of applications that are closer to data warehousing and data marts, where you just need to produce a report and you need to produce that report quickly. And in those workloads, the advantage over data warehouses is really that you can do it on top of the same data that powers your applications. So you don't need to extract your data, put it into the data warehouse, but you do it on the data that sits in the database. So the advantage is really simplicity. So that's more from the technology standpoint. And now finally, there are use cases by industry. That's the third layer. And we're mostly the most successful in financial services and media. But recently, for example, we also see healthcare coming in more and more into the platform. So, and the specific use cases by industry are different. So for example, in the financial services, we see wealth management, portfolio management, risk analysis taking a substantial portion of the workloads that we support. Versus in media, it's all about advertising and streaming, understanding the quality of service, understanding the performance of your ads, and doing that in real time, and really driving decisions that will change the parameters of your advertising campaigns based on what's actually happening. And finally, across many industries, but particularly in media, it's real-time reporting of the performance of your campaigns, or things like pricing and billing. So there are companies that have massive big data workloads, and in order for them to provide billing that's up to this second, you require something like MemSQL, and nothing else will work.
Yeah, and what you were describing of being able to build a transactional application on top of a database and then be able to build reports on that same data, if you're not using a system that can support both of those workloads in tandem, then you would generally be doing something like change data capture, piping through maybe a Kafka topic that then lands into a data warehouse to be able to have some transformation that rolls it into an aggregated report, which automatically adds latency because of all of the additional steps, whereas being able to run across the same records as they're being written reduces the overall amount of time and effort in terms of building the reports and in terms of supporting the data life cycles. And I also know that MemSQL is built to be multi-tenant, so I'm wondering if the typical case is that one deployment of MemSQL will be used for backing multiple different applications, and then reports are built to be able to combine the data across those applications in that engine, or if it's something where an additional step is necessary to be able to aggregate the data across those different applications because of some boundaries in place because of the multi-tenancy.
Yeah, so this is a loaded question. So let me answer one by one. So first of all, you're absolutely right. And in many cases, in order to provide reporting on top of the operational data, you need to set up an architecture that looks like having change data capture, piping it through an ETL tool, or in your case to Kafka, pushing into a data warehouse. Data warehouse is not transactional, so you need to be very diligent into making sure that the data that goes into the data warehouse is in fact a real copy of the data produced by the operational system. You can't just apply a change data capture log to a data warehouse on a high throughput, high performance transactional system. And the second question was around multi-tenancy, and we see a mix. Actually, we see there's a class of workloads which we call tier ones, and tier one workloads they have very, very strict reliability and performance requirements. They usually have to run 24/7. The uptime has to be 5 nines, and the latency, and especially P90 latencies, have to be very, very consistent. And so what ends up happening, the tier one workloads are typically run in separate clusters of MemSQL because they're so important to the business that any disruption that will affect those P9 latencies, or any disruption that will be affected by bringing new applications into the platform, cannot be tolerated. And then for tier two workloads, that's precisely right. People just bring a lot of applications into the platform and drive a lot of ROI through consolidation, because MemSQL is scalable, so you can bring and gives you so much compute and storage, so you can just bring a lot of applications into the single platform. Now, from the product standpoint, that motion, which we're very, very excited about, right? Because what we see in the typical enterprise is a problem that we call proliferation of data stores. A very typical conversation with something like a big bank, or a very large enterprise company, or a very large, world-class technology company. When you talk to their DevOps people, they say, look, it looks like our business team is falling in love with your technology, but we're a DevOps team, and we're currently supporting 40 plus databases. If we bring you in, something needs to go. And this is a great conversation, because we typically see several, not just one, technologies, especially legacy technologies, disappear once people onboard MemSQL.
And in addition to being able to run both the transactional and the analytical loads on the single engine, there are also additional features built into MemSQL itself, such as an ingestion pipeline for being able to consume data from external sources and pull it in for being able to build those reports. And I'm wondering what the benefits are of having that built into the database engine versus using some of the pre-existing platforms and tooling such as the ETL systems or streaming data systems such as Kafka or Spark?
Yeah, this is a great question. And you can either put a purist hat when you start looking at this from the product standpoint and say, look, we're building a perfect engine and we're going to focus on the engine and then hope that the ecosystem will build tools around that engine to use it efficiently. And then there's reality. And reality is such that the market and the set of technologies are moving so fast that the customer is confused. There's too much stuff, and that stuff is not necessarily working very well. I guess there are clusters of technologies that are working very well together, some around clouds, some around the Hadoop ecosystem, some around kind of old school legacy databases. But the observation here is that in the past, we had a well-defined interchange protocol. This is called ODBC. And once you implement ODBC, you automatically compatible with a set of tools that matter. And in the past, those tools were mostly, databases, data warehouses, ETL tools, caches. Now, if you look at the data landscape now, you realize that a lot of data sources have become distributed. We're living in the world of distributed primary storage, such as enterprise storage, secondary storage, such as object stores, which is distributed, message buses like Kafka and Kinesis. And there is no such thing as a distributed ODBC, and which means that you have a choice, right? You either wait or you bring that ingestion capabilities as a first-class citizen, which for the customer means simplicity. And if you have data coming from Kafka or you have data in S3 or HDFS, you can literally type one command in MemSQL, and this data is flowing in MemSQL in real time with arbitrary scale. It is very, very hard to achieve the same level of integration and performance by relying on a third-party ecosystem, which, frankly, is very different from customer to customer. Some people want Informatica. Some people want Spark. Some people want MapReduce jobs. So that's really why we pulled in data ingest as a first-class citizen into the engine.
And what are some of the typical ways that you see your customers using that ingest capability built into the engine where they don't necessarily have to bolt on these additional systems to be able to provide additional data sources to the primary storage system that they're using within MemSQL?
Yeah, great question. So the number one is simply load data from S3 or HDFS. This is not particularly groundbreaking, but it's incredibly easy to do and incredibly performant to do it in MemSQL. The second one is extending that capability to supporting Kafka. So now you can just point at Kafka and say, hey, move that data into a table in MemSQL, and we'll do it with great performance. We have customers that are moving that data into MemSQL tables, multiple gigabytes a second. And then the third tier to actually grabbing data from a streaming data source such as Kafka and moving into a stored procedure. So now there's control flow, and you can grab a data stream and then transform it and write it back into MemSQL or route it back into S3 or HDFS. And that supports a large variety of streaming workloads. Workloads like, I want to scrape Amazon prices, which are constantly changing, and I want to match those prices, or I want to make sure I beat those prices for the most traded products that are in Amazon. And with MemSQL, it's trivial to implement that application. Well, as long as you figure out how to scrape the prices and put them into Kafka. So now, once they're in Kafka, you can grab that data stream, move it into a stored procedure, run a bunch of SQL commands, and in transactional systems, you can have running counts, or you can store all the historical data, and you can crunch reports over that historical data with very high performance. And so fundamentally, in order to build such a high value application, you need just a few moving parts.
And on that ingestion path, do you automatically introspect the schema of the data records that are flowing in, or do you require some integration with, for instance, the Kafka schema registry for being able to determine the shape and types of data that are coming in? And then lastly, curious what the serialization formats are that you support for that ingestion workload.
So this is evolving. Right now, we support CSV, TSV format, Avro, and JSON. And in the future, we'll be adding Parquet, which seems to be one of the most requested features. And in terms of the schema, MemSQL is a relational database, so data is structured, but it also supports semi-structured data. We support a JSON data type, and when we store JSON in MemSQL, we automatically parse it and shred it and store it in a column store. So what it gives the user the ability to have as much structure as the user needs and wants, but at the same time, it doesn't sacrifice performance. So we don't prescribe to using schema to a user, but there are certain advantages in using schema, mostly around discoverability and compatibility with BI tools, where if you schematize your data and then you attach a BI tool, you clearly see what's there, and then you can easily craft visualizations, and it simplifies building apps as well. As for Kafka Schema Registry, that is something that is on the roadmap, but not currently supported with MemSQL 6.5.
And moving on to the structure of the database itself, I'm wondering if you can discuss how it is architected internally and how that has evolved over the years that you've been developing it from that first 1.0 release.
Yeah, definitely. So a lot of things stayed starting 1.0 release, and a lot of things evolved. One of the things that we quickly realized, and back to my comment around the RAM prices, is that RAM is not enough. And we made a decision back then to invest into very dense on-disk data structures that would support reporting as well as operational workloads. And we had a choice back then what kind of data structures to introduce, and we landed on column stores. In hindsight, I think this was a very, very good decision, but it took us years to get it into a place where we're really happy. And I think it's in a good spot right now, but wait for another year or so, and it's just going to be magical. So the architecture is a distributed architecture, and the hard parts are transactionality, and the other hard part is query processing. Because query processing, in order to be efficient, requires to as you run and execute a specific query, it requires you to move data around the cluster. And then, as opposed to a single node system, where one of the hardest components is a query optimizer, in a distributed system, it's still one of the hardest components, but the number of choices is much greater than it is in a single node system. Where on a single node system, you think about join order. It's kind of one of the key components of a query optimizer. Then you think about rewrites of, decorrelating subqueries and whatnot. In a distributed system, the number of choices for your joins is greater because you introduce the notion of a broadcast join, where you take a smaller table and send it to all the nodes in the cluster to perform a join, or a shuffle join, where you move data in the system before you join two tables. As well as you can say, the data set is relatively small, and I'm just going to bring all that data into one node and perform the join there. So all of that are choices, and the query optimizer working in tandem with the query execution system have to make those choices, cost them, and at the end of the day, deliver on wide variety of workloads, starting from very simple ones, kind of key value workloads, to mixed workloads, to mostly analytical and reporting workloads. So the architecture of the system has to be very componentized, that you can build and storage, query optimization, and query execution has to work in tandem in such a cluster.
And given that it is distributed by nature, I'm wondering where it falls along the axes of the CAP theorem, since there are some gradations along there that you can optimize for.
Absolutely. Well, it's a CP system, right? And we sacrifice a little bit of unavailability or availability to deliver on consistency and partition tolerance. In practicality, there's a trade-off, right? So do you push complexity on the application developer and deliver on the A part of the CAP theorem, or you build a consistent system? And it has to be partition tolerance, of course, because the greatest sin of a database is to lose data or produce wrong results. So that's really a choice. And in practice, and we know that by running tier one workloads for some of the most demanding customers, 100% availability is impossible. Even if the architecture allows that, there are certain things that you cannot control, that you cannot build a 100% available system. So it's actually a very natural choice to build a CP system, because by doing things like adding more resiliency on the hardware side, adding more resiliency in the software, adding auto-healing features, you actually drive the total availability of the platform way above the 5 nines. And going beyond that is pretty much impractical, even if you have a perfect architecture and have an AD system.
And as you mentioned, the disk storage is column oriented. And when reading through the documentation, I noticed that the in-memory representation is row oriented. So I'm wondering how much overhead is introduced by converting between those representations, between the on-disk and in-memory representations, and the benefits of having those different views of the underlying data.
This is a very technical question, and I'm going to give a very, very technical answer as well. So first of all, when you run a lot of updates, so you run a lot of inserts into a column store table, it does make sense to have a row store representation for that highly volatile part of the data. And then on the right code path, there is a certain amount of overhead of flushing that row store data into a column store system. Surprisingly, the bottleneck there is IO, not CPU. And the reason to that is the CPUs are actually very performant, and they're fantastic compression algorithms developed that are very, very cheap on the CPU. So this is part one. Probably there's going to be about 5 parts to in answering that question. The second part is, okay, well, we run a query against a column store table, and we send in the results back, and then we use an intermediate computation to produce the results of that query. If it's a reporting query, the amount of data you process is drastically more than the amount of data you send back. And in this case, column stores are the perfect representation, because we keep that vectorized representation throughout the query execution pipeline. So each database operator is running computations on top of what we internally call vector projections. And if you want to see have the analogy in the open source world, the project that's called Apache Arrow comes to mind. So all the internal query processing runs on vectors. And then at the very end, we convert that representation to a row store representation, because the client expects data coming row by row. There's one scenario in which this doesn't work that well, and that scenario is when you're trying to pull out a lot of data out of the system. And the typical way where people use it is in data science. They have Python tools, and all they want is to run a simple query, maybe with a predicate and whatnot. And all they want is to get data out of the system and move it into a Python library or Spark. With Spark, we can do it in parallel, so the problem there is not as pronounced. But in Python, we need to grab a lot of data in the column store format and move it to a Python library that's also processing data into a column store format. And in the middle, there's a client that consumes data row by row. So this is one scenario where I feel like we could do a better job, and there is a real overhead converting from column store representation to row store representation. Then there's another workload where you run high volume of updates, and in this case, our caching systems and And our row store representation is a perfect representation. We have customers running 10 million updates a second against our row store representation. And but we basically giving you an unlimited capacity for workloads like this. That's again where row store works super, super well. So having those two representation as with row store and column store allows us to cover a wide range of workloads. And depending on the workload, you can get the best of both worlds.
And given this duality of the representation for the data, I'm wondering how that translates into any special approach necessary for data modeling and building the schema for the data store, or if because of the fact that it's largely SQL oriented and relational in nature, you would just use the traditional techniques and mechanisms that anybody familiar with legacy and traditional SQL databases would be familiar with?
Yeah, it's a very good question. So we currently give you a few choices. We currently give you the ability to create a column store table that will reside on disk and be cached in memory. And we give you the option of building an in-memory row store table. We're working very hard into merging the two over time. And the reason for us to do it is just simplicity. So by giving you that choice, we're increasing the cognitive overhead for a developer to understand her workload one notch deeper to make those choices. And then we also give you a knob to define how you distribute data against across the cluster. And it's up to you if you want to use that knob or not. So barring those is just standard SQL. And then it's standard SQL, it's query optimization and query execution that makes sure that you will get great out-of-the-box experience with the product. Are we done? Well, in the future, I believe databases will get into a place where there are no choices, right? You just create tables and there's no capacity. You don't think about capacity. It's just a cloud API, which is SQL, and you can create table and run queries. And what you pay for is basically latencies. And if you latencies and the volumes of data stored and processed. We're still far away from that future, but we absolutely driving towards that future.
And in terms of the write path for data from the read path, obviously you have it stored in disk and then you do that translation to the in-memory representation. But for writing the data, I'm curious what the overall lifecycle is, given that it is an in-memory capable database and you do have that transaction log for persistence and just how it flows from somebody issuing that request through to it actually being fully persisted on disk.
So let's say you run an insert statement into a table. So when you do that, the data moves into one of the nodes in the database, gets replicated to another node. And once that happens, you get an acknowledgement on the client that the write went through. With that, you will have a transaction log on every node registering that record. And now that record is appended to the transaction log. So the data is not going anywhere. So now it's in the database. And then internally, that record will be represented as an in-memory record in that table. And then there is a background process that goes, and once the amount of data in the in-memory representation exceeds a certain threshold, it will perform a conversion of the in-memory representation to a non-disk representation and flush it on disk. So that's really the life cycle.
And one of the main aspects that you promote for MemSQL is the speed and performance of the overall system. And I'm wondering, what are some of the techniques that you use for being able to optimize for that overall system speed and performance across the cluster?
That's a good question. There are a lot of them. So let me bucket them into several categories. And I'll also give you an idea of what the impact is of each bucket. So the first bucket is in-memory representation and code generation. And in that bucket, if your data is in a row store format in memory, it's trivial to go and navigate to an individual row. So that takes very little overhead. But in the context of a SQL query that extracts either just one record or performs certain computation, One of the surprising aspects is that you burn compute on evaluating scalar expressions. And so that's where query compilation, and we compile queries into machine code, drives a lot of value. So that's, I would say, bucket number one. The second bucket is network optimizations. When you move data around across the cluster, if you do it in a naive way, you will burn a lot of compute on serializing and deserializing data before and after you move it across the network. So that code path has to be highly optimized. And I would say this is an example of just systems approach to building a database. And the system approach is understanding what the bottlenecks are and implementing them carefully and efficiently. So in order to drive value in that bucket, you're just looking a lot at a lot of profile data by running multiple workloads across the system, and understanding what the highest offender is and fixing that. And finally, there is a bucket around compression and vectorization, and that applies mostly to column stores and reporting. And that's the most, well architecturally designed and beautiful system that performs computations on top of compressed and encoded data. And that specifically is applicable for larger reporting queries, for predicate evaluation, and for evaluating joins. So one of the recent benchmarks that we published was, trillion rows a second benchmark. That's only possible by having a very careful implementation of operations on compressed and encoded data. And we obviously didn't just do it for that specific query. We built a general purpose system that uses those techniques and drive performance to the variety of workloads.
I have a question here. I'm not sure if it is an interesting one or not, about the sort of ratio of open source versus proprietary code used within the project.
Great. So we're very, very practical. The majority of MemSQL.
And how much of the total implementation of MemSQL is done using custom-built code versus open source projects that are leveraged within the engine?
I never ran the count. Certainly, we use open source software when it makes sense. The majority of MemSQL, that would guess about 95 to 97%, is built in-house. However, there are particular pieces of open source code that we use in the engine. Specifically from Postgres, we use a parser and binder. So everybody understands what a parser is. You get in a SQL query and you need to understand what's in the query. So you need to parse it. The binder is another component that is adjacent to parser that takes the query and binds it to your metadata. So if you reference a column in your SQL query, you need to know what column that is in your metadata catalog. We also use a few libraries in our column store representation, things like LZ4 for compression purposes. And we use a geospatial library from Google, I believe it's called S2, for geospatial capabilities. So that's about it. The rest of the engine, query optimization, query execution, storage, replication, all the SQL supports and built-ins are built in-house.
And one thing that we didn't touch on yet is the fact that the interface for MemSQL uses the MySQL wire protocol. And I'm wondering what you see as being the benefit of choosing that dialect for the communication layer, and if you have any thoughts of the level of difficulty or practicality of implementing additional wire protocols for people who want to be able to use MemSQL as a drop-in replacement for other database engines.
This is a great question, and people often confuse wire protocol and syntax. So wire protocol is actually very, very straightforward. You connect to a database, you have a handshake, and then the protocol is I send you a string and you give me results back. And then there's syntax. And the syntax is, well, what's actually in the string? And the compatibility certainly has two parts to it. One is the compatibility around the wire protocol, where my strong opinion is doesn't really matter what the protocol is. And you want to choose something that's the most ubiquitous and the easiest to install. And when we started, we had the option of MySQL or Postgres to be the wire protocol. And we chose MySQL because MySQL at the time was the most popular database, relational database in the world. It actually still is. But Postgres is growing rapidly. So, if we started a company in 2018, we would have a lot more pressure or pull to choose Postgres wire protocol. Then there is database compatibility or app compatibility. And 100% compatibility is only possible if you're reusing the full top part of the database. So something like AWS Aurora would be compatible with MySQL simply because they run the top part of MySQL. And by the top part, I mean everything but storage. Now, if we were to choose a Postgres wire protocol or any other protocol, that still would be two parts, right? What you connect to MemSQL with, and second is it actually compatible with 100% Postgres applications? So, and that's where you have a trade-off. You either say, I'm going to innovate on query processing, and for that, I need to build it from first principles and from ground up, or I will be driving towards app compatibility and no surprises for an application developer. And in this world, you will have to reuse the full code, and building a distributed query processor is actually very, very tricky and a hard proposition. So we chose the former. We chose to innovate on query processing, and that's why we're not 100% compatible with any other database. We support SQL, but if you want to move your application from MySQL or Postgres or Oracle, you will have to put some work. Not much, but that work will be required.
And for somebody who is interested in moving to using MemSQL, I'm wondering what's involved in actually getting an instance set up and deployed and integrated with their application and environment.
The setting up and deploying is trivial. We do a very good job. And once you commit to certain size of the cluster, it's basically a push button experience. And MemSQL will be running on that cluster. With MemSQL has no dependencies, so it runs as a Linux binary and stitches itself to a cluster. Moving an application really depends on how much this application has ties with the database. We're working with some large customers, moving data from Sybase and moving data from HANA, and the complexity of that workload usually depends on the complexity of the stored procedures. In the past, we didn't support stored procedures and we couldn't even touch those workloads. But now that we do, there's a migration path to moving the stored procedures because our stored procedure language is, though familiar, still modern. And those legacy engines, there are certain choices that they made to building a language that just don't make sense in the modern world anymore. So as we look forward to providing a great developer experience, building new applications is very, very nice. Migrating legacy applications will incur some pain, mostly around stored procedures, but those are very well understood pains, and with some effort, and if you need with some help with professional services on MemSQL, it's a very easy proposition.
And what have you found to be some of the common points of confusion or common difficulties that your customers encounter when they're either migrating to MemSQL or building on top of it with a new project?
Well, it's basically understanding the distributed nature of the system. Once it clicks, it becomes, we start to have a lot of fans on the other side of the enterprise. We call them champions. So getting around and making a leap from a single node system to a distributed system is the hardest. And once you're there and once you realize the value, then not only we have kind of passionate fans in the enterprises, they tend to get promoted too.
And going back a bit to earlier, you were saying how MemSQL provides limitless compute and storage. And I'm wondering what the capacity is in terms of auto scaling natively to the database versus how much of that is necessary to be implemented as another layer that the operations team manages. And then also, I'm curious what the licensing model is in terms of the way that the in-memory capability scalability plays into the overall system?
Great question. So MemSQL is scalable, but not fully elastic yet. So there are limits to how far you can expand the cluster from the starting point. And typically you can, if you commit to a cluster of size, let's say 5 nodes, you will be able to comfortably grow it to about 20 nodes, but not to 1,000 nodes. And but that's basically a feature, and that feature is on the roadmap. And few customers actually want to have that level of elasticity. And that's why the feature is on the roadmap and will in the future make MemSQL fully elastic.
Just curious about the licensing model as far as in-memory versus on disk and how that plays in.
Yeah, and the licensing model is per node. So it's very, very straightforward. So you basically take the number of nodes and multiply it by a number.
And what have you found to be some of the most challenging or unexpected aspects of building and growing the technical and business aspects of MemSQL?
There are a few. One is we didn't realize we didn't know viscerally what it takes to support tier 1 workloads and what kind of pressure it puts on the quality of the technology and the software, as well as the capability of the organization, which is around support, customer success, and kind of 360 customer experience that you need to have to make your tier 1 customer successful. So it was a journey, and that journey involved waking up at 4 a.m. in the morning and giving CIOs and CTOs on the other end my personal phone number, and building out multiple levels of support, in-house escalation paths, remote offices around the globe to have a very quick, basically instant response to our most demanding customers and most demanding, kind of one of the world's most demanding applications. So that's that path. Anybody who's building a strong operational database with tier 1 capabilities will have to go and walk that path. So the path is not easy, but we well underway. And in a way, that was a bit of a surprise to me, I have to say.
And given the strengths and flexibility of MemSQL, it's easy to fall into the trap of thinking that it will solve everyone's problems. But when is it the wrong choice for a particular data workload or a data platform implementation?
At this point in time, MemSQL works very well when you have a scale problem. And there are workloads for which MemSQL is an overkill, and you're better off with some sort of commodity database such as Postgres. This will change over time, where MemSQL will take over those workloads as well, simply because it will provide better developer experience and simplicity and cost. But at the time, those very simple departmental databases where you don't expect much from the database itself are better served with something like Postgres.
And what are some of the features or improvements that you have planned for the future of MemSQL, both the product and the company?
Great question. So we want to build a next-rate database company, and the way we think about features is, what are the things that we need to build to keep our existing customers happy and keep advancing MemSQL inside those enterprises. MemSQL is an enterprise company. And what are the features we adding to capture new workloads and new markets? And the end state is where you, like I said, you have a cloud service, you have a SQL API to it, and that SQL API to it has endless capacity, and you can pay for better latencies and better throughput. So on the way towards that vision, we're investing in managed services, Kubernetes integration, and we can constantly strengthening the engine itself, making it more elastic, making it more robust, having the ability to run on multiple data centers, and just driving the quality and developer experience up.
And are there any other aspects of MemSQL, the project, or the data management space in general that we didn't cover yet, which you think we should discuss before we close out the show?
Well, I think there's there's a lot of things in data management that are happening in the intersection of things on various boundaries. One is cloud to on-premises boundary, where I think Kubernetes is one of those technologies that will start supporting data infrastructure, not just stateless apps. And we're looking forward to that. There's another boundary in data management that is between databases and data warehouses, where we believe that over time we will live in more of a converged world, where you just have a SQL API to your data. And there's another boundary, which is data science to a data management tool, and the requirements for that boundary are keep rising, especially with AI and ML workloads. And I think we're just at the beginning of that world. And there's a lot of innovation and a lot of changes are going to happen around that boundary. AI and ML workloads are rising exponentially, but they need to store data somewhere. And there is no default choice for that just yet. So that's an exciting world, and we're absolutely going to be part of that.
And for anybody who wants to get in touch with you and follow the work that you're up to, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Well, I think it's that ability to seamlessly scale your workloads. So I remember using MySQL for the first time in my life, and that was back in the 90s. And it felt like magic. It felt that there's a technology that I can throw my data into, and it's safe, it's secure, and it's fast. Fast forward, almost 20 years, we need to have similar tools for exponentially more larger data sets, where when you run those commands, when you operate those data sets, it seems completely fluid and effortless. And we're just not there. Once you start operating and managing terabytes and petabytes of data, that fluidity is gone, but there's a tremendous amount of value in supporting such workloads. So I think there is a gap there, and we as a technology industry are not quite there, and we're working on it.
All right. Well, thank you very much for taking the time today to discuss the work that you've been doing with MemSQL. It's definitely a very impressive product and one that seems to be driving a lot of value for a lot of companies. So thank you for that, and I hope you enjoy the rest of your day.
Thank you, Tobias.